Thank you for inviting me here. This is a great pleasure to come to a school more than anything else. I've spent the last decade or so finding great joy in giving talks on neutron scattering. I was asked to expand from neutrons into other quantum beams, and as we've just seen, it's very hard to do all of that in an hour. So I apologize. I'm going to go very fast, actually, through neutrons as well as muons, synchrotrons, and NMR. But I hope to give you a flavor of what we see in these microscopic probes in frustrated magnets. And I don't actually say much about quantum spin liquids. I think to address the question earlier, theorists are wonderful at creating new spin liquids continuously. You know, they take a model and they do the wonderful mathematics, and they can come up with a named liquid. As was explained, experimentally, that's actually very difficult to start naming your liquids. And in principle, when our techniques get better and we spend more time at it, we probably can. And there's some new liquids where we're heading that way. But in general, as an experimentalist, and at every frustrated magnet meeting that I go to, someone always says, to the experimentalist, what do you mean by this liquid? And you get the same answer. It doesn't order. Unfortunately, language is also wonderful, especially the evil English language. And a lot of people in this depiction here of data maybe will take a point in the middle here and call that a liquid, although it orders later on. But there's characteristics at that given temperature or field, which you can explain with basic liquid theories, and so we like doing that. And one of my examples, research I did many years ago, was on what I started off calling a cooperative paramagnet. So it's a very classical name, which basically is a paramagnet with some cooperation, some exchange of knowledge on a short-range basis. Over time, colleagues have started calling that a quantum magnet and a quantum spin ice, which wasn't mentioned earlier, but a different type of magnet. And so we get very mixed up, frustrated in our languages sometimes. And some of that, unfortunately, is just due to the need to be published, and so we hype these things. I think one of the slides earlier says, it was something like complex or exotic magnetism rather than quantum spin liquid. And what we look for is away from the normal. Right, so we're now in this date and time, and to get a PRL, we can't publish a simple ferromagnet, even if you use the most exotic technique in the world. So we look for things outside the normal. So I do neutron scattering. As an instrument scientist, I'm employed to look after an instrument and take care of users that come by and do things on my machine. I've been a frustrated instrument scientist because I also wanted to do my own personal research, and that happened to fall into frustrated magnets from way back when I was in graduate school. So my evening job, weekend job, and that was to do more of the real science, and in the day job, what they paid me to do was to look after an instrument once upon a time in that institute. Within a neutron institute, there are many instruments, and unfortunately, to understand a material, especially as complex as a frustrated magnet, you have to use many of these instruments. So I was working on this machine, but used this chopper spectrometer a lot to look at excitations. There's a diffractometer down here to look at structures. If you're looking at skyrmions, you'll start to use these machines. As I will try to tell you, and it was alluded to you earlier, the low energy dynamics is critical now to these spin wave theories, spin liquid theories. And to get low energies in neutrons, you either have to use my machine or what we call a backscattering machine. The more traditional triple axis and time of flight will look at the higher energy scales. And to some extent, that's like looking at the mean field theory Curie-Weiss side of things and not the more exotic low energy scales that are going on. And in the end, we end up doing very complex, very difficult studies to try and understand these. So we often have to perturb the ground state, as was mentioned, break those valence bonds or so, and look at the excitations. And it was much easier to just look at the ground state. But in quantum materials, especially the quantum liquids, that becomes impossible. So I have to catch up with time and to go on. If I was giving my neutron presentation, it would be between 1 and 3 hours, and I have 15 minutes. But there are many properties of the neutrons you can check out in textbooks, and so that tell you that it's a wonderful probe. One of the main ones is the wavelengths associated with neutrons that you'll get at facilities. Is same as synchrotrons in X-rays or with electrons, and so is that the wavelengths associated with them is ideal for the spacing of atoms. So you can start to look at correlations within them. With neutrons, these wavelength neutrons have MEV, small MEV kind of energies. And that's the appropriate energies for many of these excitations when we were talking about spin waves and ferromagnets and so on. Whereas in X-rays, it's actually kiloelectron volts. So to probe something with millielectron volts accuracy, you have to build a very modern instrument. And some people would say it's to get to 1 MeV is basically impossible. But you have to take a beam with KeV and make a resolution of MeV, whereas neutrons already have the MeV, and we go from there. With the neutrons, depending on what tools you use at home or what you read, 1 MeV has about 8 wave numbers for those in light scattering, or a quarter of a terahertz, or close to 12 Kelvin. So these are the kind of energies that we know are appropriate for thermal excitations and spin waves and so on. For us, in this magnetism meeting, another important thing is that the neutron has a dipole moment, and so we can probe the spins in our system directly. So that's our biggest strength. And because of some of its other properties, we can actually have very complex sample environments. So until more recently, X-rays and other facilities couldn't do things at dilution temperatures, and we're kind of stuck at maybe 20 Kelvin. If you had a fantastic machine 20 years ago at a synchrotron, you got to maybe 4 Kelvin. As we know from what we're studying today, that would be a disaster for quantum spin liquids. That has changed. They put everything in a great big vacuum tank, so you can imagine this huge spectrometer with the dilution and everything inside a vacuum. It gets very complicated, and more often than not, things don't work. The other problem with synchrotrons still is because you're coming in with such a high energy, your beam, your synchrotron beam, will heat your sample. And we can see this quite easily by turning on and off the beam, the temperature of your sample changes. So whenever I've done a synchrotron experiment and it's failed, my local host says, beam heating. You didn't see the transition because although the thermometer says you were at 1 Kelvin, you were probably more like 4 Kelvin. So it's a very complex, and neutrons doesn't suffer from that so much. We both obey Bragg's law, so all this simple stuff you learned at school still exists, and we use this to look at spatial correlations within a sample. So how is one spin or one atom here related to this one? You get your crystal structures, but we can also look at the magnetic structure. But in general, what we are looking at and I'll stop right here, is a well-defined incoming beam. Depending on the experiment, you know its momentum and you know its energy, or maybe you only know where it's going, its momentum. And you look at the scattering probability into a certain solid angle of another beam. If you need to know its energy, you work out its energy, and then the difference in energy here is an energy transfer. And by Bragg's law, you can get the momentum transfer or the Q, so the correlations. And you come up with some of those pretty pictures you've already seen of spin waves or spin-ons and so from that. Just quickly, this is like a basic mass to it, and you're looking at some scattering strength of your material and the two states you're scattering from, or energy. With synchrotrons, you interact with the electron cloud or with X-rays. And so as you go through the periodic table, that strength increases. So if you were looking at hydrogen diffusion in iron, it would be almost impossible to see this hydrogen. So you wouldn't get the diffusion you really want. With neutrons, that interaction strength here is isotope dependent. So hydrogen and iron, actually hydrogen is much bigger. So hydrogen diffusion in metals was a huge topic many years ago, and it was mainly due to this. But it's also isotope dependent, and the classic that we show is hydrogen and deuterium that are so different. So especially in soft condensed matter, they can deuterate a sample and put deuterium in certain places in a protein crystal structure or in polymers and probe a certain area of your sample. But this is also true of iron or nickel. The isotopes change, and if you really want to get creative in your studies, you can do a nickel isotope substitution and look at nickel quantum liquids and get extra information. The more variables you have, the more information you get, and understanding it all becomes the trick. But sometimes with these substitutions, you make a complex puzzle a little bit simpler. So I do later on, but I can say that here too. So this is the scattering power. There's also an absorption power. So with neutrons, certain elements actually absorb neutrons and don't scatter them. So in your detector, you get a very small number. Gadolinium, which is going to be my example later on, is one of those materials. So you can get around it by using a different isotope, which gets very expensive. And so only crazy people like myself do it. And iridium's another, or boron, and you tend to find ways around it. It's an absorption of the beam inside your material. So one way to do it is, instead of doing transmission geometry, which is our normal, where you shine the beam in and you scatter out here, you can do everything in reflection. So then the beam only goes in a micron or a millimeter. You can decide that. The other one is to buy expensive chemicals. I've recently done an experiment where we basically polished the sample down until it was thin enough so that we could scatter through it. But it means also neutrons are a low flux technique compared to, say, your X-ray sources. So you need time to compensate for a lack of material in the beam. So if you start shaving it off or do things in reflection, you have to ask these user programs for a lot more time. And then they have to weigh up, well, I can give Jason 3 weeks to do one experiment, which maybe becomes a paper, or I can use the 3 weeks to do 10 experiments with a 30% chance of a paper. Which one should we do? And that's part of the politics of the game. This is another neutron X-ray comparison that we don't look at. In real space, looking at imaging with that hydrogen scattering, you can see water going into plants or fuel cell research, or you see here a photograph, but behind here there's a piece of metal hidden. So with contrast matching, you can see a lot. The math I'll skip. I know tomorrow you'll see more of it. We basically break it down through this double differential. If you don't want energy, you can go back a step to stuff associated with your instrument, your final beam and your incident beam, and then the physics is all in here. And in magnetism, that can be related to the inverse susceptibility. So some of the great things now that we're doing, actually we did them years ago when we were studying spin glasses, where you want to look over a wide range of fluctuation rates. We would compare AC susceptibility with NMR, with neutrons, and you'd have these beautiful plots over 4 or 5 decades in time. We kind of stopped doing that for a while, and we're going back to it with the interest in quantum math. To understand these emergent phenomena, you need to look at things both in Q space and energy space over many decades. So the Ni gas was one of your examples, nickel gallium sulfide. We've just published a couple of years now maybe, where we used NMR, muons, neutrons, and susceptibility to understand the system. And any one of those, you could write a paper, this is what neutrons say, this is what NMR says, but they would be very different. And it's only when you got all 4 probes, we know physics, everything has to agree with each other in the end to really understand it. There's only one Hamiltonian for the system. By understanding that, we were able to publish it. Yes, that's triangular lattice. So from scattering or from neutrons or X-rays, we can do the diffraction. So here we don't care about energy, and we look at crystal structures or spin structures. We can work out the arrangement of ferromagnets and antiferromagnets from where the Bragg peaks appear. And these are, there's lots of software now that easily does that. You run through to minimize the fitting, and you're looking for the intensities and the positions to get all the information. And you see with neutrons here on a pyrochlore, over a wide range, you can get a lot of information on the crystal structure. And from this, we were able to say this pyrochlore, which is a glassy pyrochlore, has a well-defined crystal structure. Now, I say that here, and I correct myself later. This is a bulk measurement. You put 3 grams, 5 grams, 10 grams of material in your beam, and this is the average structure. And you refine it with the average. If you're an aficionado and you really care, you can start looking at the background down here. It's called pair distribution function analysis, or total scattering. And in this background, you'll see lots of data isn't on the fit. And that will be local disorder. And so we'll look at that a bit later on. But in diffraction terms, you get an average of the structure. Inelastic neutron scattering, where you have your elastic line, which comes from these peaks, or even here, they'll be very intense. The inelastic features, the spin waves, the magnons, the spin-ons, is at least a factor of 10 down in intensity on every material, rule of thumb. So you're looking at the background position, and then you want to do the inelastic, you drop down a factor of 10. If you sit on top of the Bragg peak and you look at the inelastic, you have to go out quite far out in energy before you are invisible to that Bragg peak. And so there's a playoff at how close to these Bragg peaks do you look at. And then to get the full dispersion curve, of course, you want to move between Bragg peaks. And so you always play. But this is inelastic. It's a well-defined restoring force is needed, energy is needed to get back to the ground state. So crystal fields, spin waves, simple harmonic oscillators, phonons vibrating in your sample are all this way. And I like to say, although many people put this in here, quasi-elastic scattering is when it's almost elastic. So very small energy scales. I'll show you an example, and I think this will become more and more important to this community. It's where the instruments, if it was truly static, the instrument would give what was a red line in the middle there, very sharp peak, but the sample put in the way broadens it. And understanding that broadening is some sort of low-lying, it could be a low-lying excitation, it could be that you model it with a Gaussian in here, or it could be just a broadening of the peak. So that's, like we were saying, the lines in EPR or that will broaden because of frustration in different exchanges. It could be stuff like that. And the ones where it's broadened and not a well-defined excitation is what we are more interested in. This is the traditional stuff, so spin waves. You can, by scanning in different directions, here's in the H00 and here's in an L direction, you can work out dimensionality, so there's no dispersion here and there's lots here. And then by fitting these data, you pick your model that you think is appropriate, and you can get exchange and gap numbers. Now, of course, and this is a take-home message that I try to get across to many when I give these talks, is you read wonderful neutron scattering papers. Like I can read wonderful Hall probe and electron microscopy and that what you get in 4 pages or in 10 pages is a small part of the story. And it's only with an expert eye or a little bit more information that you pick up on these things. So I don't think there's anything wrong with this. Jeff Lynn is a good friend of mine, but they're saying there's a gap here. But you see, there's not much data down here to say that there was a gap. It could be with a better instrument resolution. There could be points down here, and it doesn't go like that. It comes there. So there's always improvements that can be made to data. There's definitely dispersion where there's no dispersion here. And whether there's 3 branches or 2 branches, that's part of understanding the models that you're fitting, etc. But they're all there. And this is another one that we don't do very well, I would say, today, but we did excellent jobs at it 20, 30 years ago, is in crystal field analysis. And with many of these rare earth pyrochlores, but also other rare earth quantum magnets, this becomes more important. It's actually the crystal field scheme that we often then say this is a quasi-spin half system. It's because of the actual way that these levels break up that we can imagine the ground state as a spin half system rather than what holmium really is, for instance. And so in neutron scattering, here's some data to a first approximation to get the energy scales. All you have to do is fit the resolution peaks and then understand its temperature dependence, and you pick up things, and Q dependence. But you see the B here is the transition from the ground state to this second set of crystal field levels. A down here is from the ground state up, but C in the middle is from the first excited state to the second, and you see its temperature dependence is not obvious like the other two. And that's because thermal energy is used to populate this before you can excite it up. So at the lowest temperatures, this peak C would vanish completely. Because your thermal energy, I says 1.8 MeV is about 30 Kelvin, so you have to go significantly below that to make the probability 0. But if you get down, even at 10, it's a small peak. If you go to 5 Kelvin, this might vanish completely. And if you go up, it will maximize when this is fully populated and then start falling down again. So all of those techniques are all in the literature, all in textbooks. Most of us will concentrate on one thing to sort of understand crystal fields with neutrons or understand crystal structures with neutrons. Very few of us are mad enough to try and do all. But, yes? So matrix elements. So as I forgot. So the first approximation to get the energy levels is just the positions. And then to actually get the scheme, the eigen values and vectors, you have to then fit intensities through it. And that's actually, for someone that's tried this several times, you make a lot of mistakes. So terbium, I'll show you later, with even some good friends in this field, we've done it several times, and we'll change the actual ground state levels. Not significantly, but it makes a big difference for those that understand crystal fields. So I'm going to now try and use the pyrochlorous gadolinium titanate and yttrium molybdenum oxide to talk about a few of these probes. Neutrons I've covered in a little bit more detail because that's what I'm an expert at. But you always, I find, especially in frustrated magnets, you need more information. It's very, very hard in any frustrated magnet to get the full story from just one probe. So here, it says, I've already said this, diffraction will give you the bulk structure, so you get this on average. And it's become very clear in the pyrochlorous structure that at the local level, it's not so beautiful in most of our pyrochlores that we've studied. And then you'll see that first showing up in the literature because Professor X says it orders and Professor Y says it doesn't, and the transition temperatures might change. But it can be as dramatic as doesn't order at all, a quantum spin liquid if you want, and an antiferromagnet with transition at 1 Kelvin, just by some sample dependence. And you'll do diffraction, and both samples will look perfect. And it's only when you get to the fine details of all these spin-to-spin bond lengths exactly the same. If there's any small difference, the energy scales that we're talking about in quantum liquids or in frustrated magnets, they're all roughly the same. And so you change one by 2%, it changes the physics of the system. And there's many examples that we now have that excites the community, but also is a bad vision to others who are just reading the literature, and they say, well, what's really going on in terbium titanate, for instance, because I've got 10 papers here with 10 different answers. Turns out that we write chemical formulas, YB2TI207, but all of them tend to have a plus X or minus delta next to them. And many physicists and material scientists don't go to the time and efforts in detail to work out exactly what those are. And 3% difference or even less can change these things dramatically. So we also have local probes, as was alluded to. So in this case, you could have NMR, where an element is your probe, really, and you measure some effects locally from that site. So when I show you some yttrium NMR in the future, that's the case there, is we use NMR to probe the nucleus of this yttrium, and we look at its surroundings. But it's not long range, it's not the average bulk. You can actually start to see details. In muons, the muon will sit somewhere, in most cases, very close to an oxygen. Where that is always a controversy on the studies, but it will sit, so it sits in an interstitial site. And there might be many of them in a system, and they have to work out what is going on there. So those are local probes. You can also get the local structure or so from this total scattering approach to neutrons, where you really look at the background, where most of us throw the background away. It's just too much work to look at. Or X-rays can do that. And then there's a technique where I'll show where XAFs, where you tune your synchrotron to a given energy, which is appropriate for a valence state of an element. So in my case, I'm going to show you molybdenum and yttrium. So it's at different energies in that spectrum. But at that energy, or close to that energy, there's a resonance, so a huge increase in the scattering power. And from that, you can then look at the local environment around there and get some numbers. Gadolinium, I started studying it. As it says, it's very expensive. My samples are on the order of 100 microns, 100 milligrams. If you spend a lot of money, you can make crystals. We discovered that that wasn't always the best thing to do. Because of the absorption, we have to buy these expensive compounds where they've removed the absorbing isotope. It does have a large moment, which is a saving grace, so the scattering power is huge. So even with the small samples, we can get some data, as I'll show. If we were doing this with copper, with a spin half, we would be completely lost at 50 milligrams. It gets really hard. And I started this because there was a Palmer-Chocker model out there where, I was chasing, like we chase spin liquid models. There was this thing that says that an antiferromagnetically coupled spin on a pyrochlore lattice, quantum or classical, will not order. All the models will show that if it's just a J, it remains a quantum spin liquid if you want. But if you have any perturbation from that, then it picks an ordering wave vector and you get ordering. And Palmer-Chocker, for things like gadolinium with a big moment and therefore dipole interactions, showed that there was this unique ordering for this quasi Heisenberg system of gadolinium in the pyrochlore lattice. The anisotropy, the single ion anisotropy of gadolinium, in most of our classes we'll say is 0. But when we really look at it, it depends on the environment. There's back to crystal fields. And the rare earth environment of the pyrochlores is trigonal. So actually there's it can be significant anisotropy. And actually I don't have it in this slide, but if this was the rare earth A site, in the middle of every tetrahedron, there's an oxygen. And this is critical to pyrochlore physics, especially the rare earth pyrochlores, because that basically means that the spin on this, say this ball here, with an oxygen here and here, will either, because of crystal fields, want to point directly at the oxygen or perpendicular to it. So you find that most of our samples are either Ising-like antiferromagnets, as I'll show, or XY-like, where the spins are in this plane perpendicular to the two oxygens, or it's Ising because it either points in or out of the tetrahedron. So that was the math. If we just have Heisenberg, and then we can add the dipolar, and there should be no gap. So like you saw in the previous talk, all these good, interesting systems at the high temperature limits looks like a normal magnet. And many of them will fit Curie-Weiss law, mean field theory wonderfully. And that's a way to get this interaction strength at the paramagnetic limits. It's not always measured properly, but if you get to truly the paramagnetic limit, you'll get this interaction strength, which then if you compare nearest neighbors, you get a measure of J. It's really a measure of all the exchanges, so sometimes the next nearest neighbor is stronger, and that will throw things off, but it's a good measure of the strengths in the system. And so we always will show, so in gadolinium titanate here, and this is stannate, they're both roughly 10. So all we've done is change the B site from one non-magnetic to another. The lattice changes by 3%. The A is a cubic system, so the A lattice changes by 3%. In gadolinium titanate, we see 2 transitions. So already this Palmer-Chocker model is wrong. if you're just looking at this system, it predicted one transition into a well-defined state. In the stannate, there's one nice transition, which is a good sign. And depending on how low in temperature you can get your data, so the green was first, you can say this is nice and linear. You can do some of the modeling that was discussed earlier, and you say there's a lot of degeneracy, it's gapped, it's not gapped, whatnot. If you're able to get more data, then you can reduce the number of models. And then in this system, you have to worry about a nuclear contribution for this small little upturn. But now we believe if we just had this, it says the first paper was published, they says it was had residual spin dynamics. The second, no, this is the titanate and this is the stannate. And so when we saw the stannate with only one transition, we thought Palmer-Chocka might be correct, but we've done the measurements on both. So here is some more, so this is the susceptibility. The stannate, there's one transition, but then when we do field cooled, zero field cooled, there's a splitting, so that's not normal for an ordered antiferromagnet, so that already starts to bring in questions. In the titanate, there's splitting, and there's also a kink here, suggesting a second transition, which we had previously seen in the heat capacity. Here, this is another experimental artifact. If you have a polycrystalline system and you're doing heat capacity at the lowest temperatures, getting your sample into thermal equilibrium is very hard. And if you're in a rush, your grad student's doing it and just wants to do one a day or so, you end up with data like these black dots, where the critical first transition is there. But the second one, this was a broad feature, but there was no real peak here. When we have a single crystal, so you can isolate it very well, you see that this peak is nice. So here's some neutrons. And here I only show magnetic diffraction. I've removed the crystal structure. So we have lots of nice peaks. Whether you look at all my data in this color contour plot or at one given temperature, like so, you have lots of nice peaks. If you look at the intensities, you can actually see the two transitions. This is the titanate, I'm sorry. You see at high temperatures this broad bump, and these are short-range correlations. The Bragg peaks are when you have, in principle, infinite correlations, long-range order. Unfortunately, and what is now more popular in the literature today, there's especially with cubic systems, there's multiple K structures. So in a nice system, one wave vector will define the whole crystal structure. Sometimes you need two, so you have two wave vectors to define it. In the pyrochlores, you can have many more. So here I show a 1K structure and a 4K structure. And you have 2K structures, 3K structures. And they all show exactly the same Bragg peaks. If you just calculate it, they're exactly the same. So from a powder average system, you can't distinguish them. You then think, well, let's go to a single crystal. That would be brilliant. And then you remember that there's domains. So if you have multiple domains, you're not exactly a powder average, but you've got some averaging. So we tried that didn't work. We still had many answers. So we've, as I'll show, we've tried several other things. But from diffraction alone, we can speculate, or if we were really honest in a 10-page paper, we could show you 10 different models and say it's one of these. We often have to sort of like point to something, and we'll use other probes to try and get it correct. The stanates actually was nicer in that regard. When we did the neutron diffraction, the only model that fitted was the Palmer-Chocka model. So it's definitely got this kind of arrangement of spins. The size of the spins we can still debate. There's quite a bit of residuals in these error analysis here, but it's definitely the Palmer-Chocka model. Mossbauer says we look at other probes to try and help us. Mossbauer in titanate says there was, in this intermediate range, there was 2 different moments in the system. So that's, neutrons are saying that with multiple Ks. In the stannate, there was only 1. But in detailed analysis of these spectra, they were never in thermal equilibrium, and they would always say there was persistent spin dynamics, these words that help you think about liquids. Muons were the same. Muons get some oscillations, but not the size that you want, or not a single frequency here. There's several beating. So they always say there's persistent spin dynamics. In the stannate, it seems to be a very low number, but quite flat and not 0 in this relaxation rate. In the titanate in 0 field, it's up here, and we can see that these are real spin dynamics. These dynamics are fluctuating. We could pin them with an applied field of 5 Tesla, and you quench this persistence. So there's something there. Neutrons, we went to polarization, and this is one way where we can look at the nearest neighbor interactions, for instance. And we can then look at the 1K and 4K model and say, well, maybe the 4K is more likely. But another way to do that, which is becoming possible now with software, so we don't have to go to our theorist friends to help us calculate all these things, is with the program was shown earlier as linear spin wave theory, and there's questions about how accurate and wonderful that is, but it's a way of analyzing spectra. So out of every ground state, depending on the structure, the excitations will be different. And this is exactly what quantum spin liquids will end up looking at the end of this story. So if we look at the excitations out of the possible ground states of gadolinium titanate, we might see something. So we've done a very difficult inelastic neutron scattering experiment on our 50 milligram sample. And we see this was taken a month ago, so we haven't done any processing really of it yet. This is the elastic line where the Bragg peaks are. That's obviously a Bragg peak with this bigger bump here, and there's some more out here. But then above it, at 30 millikelvin, there's some spectral weight here. There's some scattering. That's obviously this is at 770 millikelvin. It's temperature dependent, which is a sign that it's probably magnetic. And then there's this flat band here. Maybe it's flat. You can't say much. This is powder averaged in a small sample, but it's also broader here, so maybe there's some dispersion down here, maybe there's 2 bands. In this intermediate phase, the spectra is definitely very different. Just plugging in the numbers of how we imagine the spins in the system, just the spatial correlations. For 3 different models, these are the calculated excitation spectra. So there's one with significantly high spectral weight at high energies, quite dispersive, and something down here. There's a model here where there's very flat bands at different energies, and then one finally over here where there's 2 bands. The elastic line, I'm sorry, is actually the bottom axis. This is 0 here. So all of this is excitations. So here there's 2 bands, maybe with some dispersion. So if I go back to the data, I've covered up the other 2 because I want to try and convince the readers of a paper soon that this model is appropriate to these data. So there's a flattish band at 0.2, and there's something down here, over here. There's not much up here. So we went through about 30. We just did this by brute force. We're not smart enough to do it any other way. So we went through about 30 different models, doing all the calculations. Each one takes a laptop about 2 days. So you just kept on going. And we did that. We can take these data in the models and do line plots through them. And so, but I haven't shown that. An old one that has been published is that stannate. So we take the Palma-Choca, and Michel Gingras at Waterloo had done the linear spin waves for Palma-Choca. And we took our data and fitted these peaks. And the color contour plot doesn't show too much, but the dots in here are where all these peaks are. And then the dashed lines is the Michel's theory. So we believe that, we didn't disbelieve it, but the Palmer-Chocker model seems to be appropriate for the stannate. Another technique that I use is spin echo, neutron spin echo. And all I want to say here is if you see a nice data set with a normalized scattering function on the y-axis, a ordered magnet, a conventional on-your-fridge magnet, will run across 1. So it's basically saying that your neutron beam doesn't depolarize when it goes through your system and it remains 1. At time equals 0, everything should be 1. The correlations between spins won't change if it's 0 time. So everything should start here and then relax. So in these systems, we're saying there's something that fastly relaxes and then slowly falls off. And our instruments don't allow us to probe this at the moment. But what can we get from this? Well, we see that where it does saturate is 3/4, and those models were all 3 spins static and 1 spin dynamic. So that kind of agrees there. And what we're seeing here must be the relaxation processes and the 3 that eventually become static. And the one that's dynamic must be very fast inside this range. And so, this is the fastest neutron scattering technique. It looks at things normally in polymer physics where it's very floppy, so slow dynamics. But there's a lot of dynamics that are outside our window. A model that you can read in the literature sort of like shows that this pathway here where there's a gap, so the next nearest neighbor can be J32 here through another magnetic ion or with no magnetic ion, and this is critical. So the gadolinium titanate, we believe, is in this part of the phase diagram, and the stannate is up here somewhere. And if we're smart enough through other probes or equipment with pressure, for instance, we can start to move this around with maybe single crystals. So we're looking at that. Quickly, this is a glass, but it was a glass, spin glass, where there's no disorder. If you did that diffraction pattern, there seemed to be no disorder. But it's a beautiful spin glass with a very high transition temperature for something with no disorder. And you see here the Curie-Weiss temperature is very high, so the interactions are high. If I look at a pyrochlore which is conventional, that has a ferromagnetic transition or so, if this technique called XAFS, the data is the dashed lines in the middle with the dots, and the model is over the envelope and the lines in there. In this system, our pyrochlore model fits it beautifully. In our glass, it doesn't, especially on the molybdenum edge. And to a first approximation, as someone that doesn't do XAFS, that's all I will say. But my colleagues then can parameterize this and give us some numbers that they reckon there's a 20% difference in bond length of the molybdenum sites. But on average, when you do diffraction, averages out to 0. If you do neutron PDF, you end up doing the Fourier transform and you get these peaks. And each peak you can relay to a different bond. And one of the take-home messages from this paper by Greedon was that as they cooled down this yttrium molybdenum oxide, the fitting got worse. So it was something that got worse as you cooled down. As we cooled down, we don't expect a structural phase transition. We haven't seen one. So we think what's happening is the magnetic interactions are becoming involved. You're getting correlations, and then you have magnetoelastic effects, and these bond lengths start changing. In NMR, another local probe with yttrium, these peaks, if you want, if it was a nice, wonderful system, should just then be a simple Gaussian, a nice, smooth curve. But with NMR, we saw as you cooled down, there was actually structure to these curves. And at the lowest temperature of this data set, you had many peaks. So this was telling you that around every yttrium, there was some discrete, because these are nice peaks, it's not just a big blob, discrete positions, the different internal fields well defined. And so how we've put all that together is actually that I can't do it on a corner sharing tetrahedron. My drawing abilities are useless. But on a triangular system, where if you just take the planes, we're changing these bond lengths, obviously different lengths and averages to 0, but then you get different J's amongst all of these. You have some long bonds, some shorter bonds, and the yttrium NMR is probing some sort of average, and you're getting this discrete stuff. The muons is also seeing these very confusing local fields. Neutrons at the diffraction level is seeing this long-range ordered structure. But we believe we've been able to understand all that. And going back to my first love, terbium titanate, this has a 20 Kelvin minus 20 Curie Weiss and a large moment. And this system with down to half a Kelvin susceptibility, there was no ordering. Around 50 Kelvin, there seems to be a separation from Curie-Weiss law. If you use muons, you see these persistent spin dynamics down to, I think it was 10 millikelvin we got to in this experiment. So there's obviously something going on here, which we determined in the end was a low-lying crystal field depopulating. Yeah, NMR. Yes. So, in this cartoon here, I've basically only shortened these, but the length of this must be different for many of these bonds. But it's also, we still don't really understand it, but it's discrete. So for some reason, it's going to a well-defined position, if you want, but there's many of these. If you imagine this spin here, it basically can move in discrete positions up and down here. You're changing the J or the fields that you will experience in this environment, and you're getting all those peaks. And as that data showed, as you cool down from 200 Kelvin to 92 in the transition, remember, is at 22, we imagine these correlations are building up, the strength is increasing, and you're able to detect more features. These are some cautionary tales, and also to highlight another probe you might, or another bit of physics you'll get this week. So this is a powder data set from terbium titanate, the full raw data that you'll get from the spectrometer. And all the big sharp peaks that are going up here are from the crystal structure. So that's what us in magnetism really don't want to understand or talk about. What we normally do is take a high temperature data set where we believe it's a real paramagnet and just do a simple subtraction. Oops. So if you do a simple subtraction of this data set, you get this red dots here. So this is what we call the magnetic scattering from the sample in a very cheap and easy way. It's not the best way to do it, but it works quite well. These bumps tell us about the correlation. So in this case, it told me that there was 4.6 angstrom correlations between spins, and they would get sharper in temperature if that got longer. And we never see that. It always kind of remains at this kind of broadness. If you warm up, it gets flatter. In a real paramagnet, it should be background and very flat. We all have to start somewhere, and this was great as a powder experiment, but now with single crystals, you see there's much more detail. If you probe it in different directions, you get much more. You can then model it, which is these more colorful plots. So this is the data, and this is the plot in different types of scattering. You can try and model that. And you see, this is the best we can do today. The guy that did this, is actually, he spends a long time trying to understand his data. I really trust this. But, it's clear that what you've got in the data and what you have in the model is not exactly there yet. And that's why we come to these meetings and we talk to theorists and we try to progress. These pinch points, as they're called, and we see beautifully in theory, there might be something underneath these, but it's not quite there, right? But it's giving us some ideas. No one, after 20 years of studying, no one understands what terbium titanate is a liquid. It's still, it doesn't order. And so this is the raw data. And what we do is we go to, in this case, I went to 50 Kelvin, where we assume the magnetism is obsolete as a paramagnet. And we take a data set and then we just do a subtraction. So this is a subtraction of, so that takes care of all the instrument artifacts, the crystal structure, the sample environment around you. And then I've done some binning to pull up the intensities. So you take, so like every 5 data points and average it or something like that, and you get this. This is yes. And in this case, I've actually gone through with the form factors so that we can start to model it a bit more. And then these guys have done that in a much more complicated way by doing polarized neutrons. So this truly is the magnetic scattering. It's a very complicated process that I do too. And then these models. Yeah. So these are experimental, and this is the model that they want to promote. And then this is, so this is the, I think it's these, the MY and the MZ. So it's different components of the yeah. You're not meant to see it. It's not my data. So it has become, for those that can do the modeling or to plot it, this is kind of the way. So it should be symmetric, right? What happens at -1 should happen at 1, 1. And so that's the way. Sometimes they plot it where they have just the this data and then next to it in another panel the model. Depends on how much detail is there. And to be honest, color contour plots get you science and nature articles, but they don't tell you anything about the physics. It's too much. So these are the crystallographic axes. So this is HH and this will be L planes. And there's different components of the magnetization from polarization analysis. We can talk about it later, but Tom Fennell did that in 12, so it's some time ago in terbium titanate. And really, it's I could take spin ice or really any material, a powder. In neutron scattering, if we do inelastic neutron scattering, is a 4-dimensional problem. You do a powder, you take the X, Y, and Z down to a mod Q, just a length scale, and then you can get energy, so you could have 2. In this case, it's just diffraction, so you're only looking at 1. This is really why I put terbium titanate in. Tomorrow you'll have a talk on the crystal fields of some of the pyrochlores. And just with neutron scattering, there's these huge instruments now that come in with high energy neutrons. In this case, it must have come in with something like 100 MeV, and then it looks at all the scattering from 100 down, and you get these bands. The resolution of the machine depends on that incident energy, so to get a full understanding, you have to do something like this, where it's at 10 MeV and down. This must be about 50 and down. And then a crystal field is a local probe. It's, what is happening to that terbium ion is not cooperative. So then that comes out in neutron scattering as these flat bands. It doesn't depend on Q. It's really just at that point. And so you can take these levels and then do fits or use your software of choice. And this is the titanate and stannate again, where there's a small difference in lattice parameter, but very little else. But from the calculations and the modeling of these data with heat capacity, you see that terbium titanate's crystal fields, it's 13 levels, covers 120 MeV, whereas in the stannate, everything is still significantly compressed down into like the first 50. This, as I said, remains a spin liquid, and this has an ordering temperature just below 1 Kelvin. And to date, we know crystal fields and the anisotropy in that is important, but to date, this was like the biggest difference between these two that we've really seen. In that, if we look at these stuff down here at low energy scales, there's still a lot of going on. So this is just within the first 2 MeV. This is my echo, which is really down here, and there's lots of relaxation. I think to understand quantum systems completely, we have to go that way. At the moment, and this is my last slide, we don't, as was discussed in the first talk. And like terbium titanate, there's no Bragg peaks. We don't have any long-range order. In terbium titanate, we see some blobs. Sometimes you don't even see the blobs because the correlations are so weak. But what you see is the excitations from this liquid-like state. So here's a chain system where, you know, in the ground states, there's no Bragg peaks to look at for the magnetic system, but they can get lots of nice inelastic neutron scattering. And the idea is now to model this to understand what kind of linear chain system they have. And here's the trichloride, where this is the data. They see wonderful excitation spectrums. This is at some given energy. I think it was something like 5 MeV. They have a pattern that looks like so. And this group out of Oak Ridge, this is at the moment their best model that they used in the publication, which shows you maximum intensities in the right place and blobs off to the side, but the real structure is clearly not there. And this requires more modeling, more understanding. And really, in my eyes, and I can say this from the outside, it's easy. A lot of this seems to be a materials thing. It always seems to, at the end of the day. So a good material gets you your best answers. Neutron scattering wants large crystals. Large doesn't always mean good. Understanding this 2% disorder of any type in your sample becomes critical when you're interested in such exotic systems. And I think, oh yes, I will acknowledge, I'm sure I've missed some friends that have contributed to the talk, and I'm sorry if I've missed them. I put this as a final figure. We mentioned in NMR, you're looking at the nuclear spin. Heat capacity, if you go to the lowest temperatures, then there's been many mistakes in understanding heat capacity by ignoring the nuclear spin system. And in neutrons, we can also see it if you do the toughest of experiments. So in this pyrochlore spin ice, we found these two small peaks off to the side. Here they're shown, so the Q-independent peaks. This is energy. Just to make it look nice, it went that way. And these, at the time, we haven't discussed it today. You might hear something over the next week about monopoles and a new quasi-particle excitation and spin ices. If I could determine that this was a characteristic of the monopole, I would have a Nature paper, overnight, so they would love it. But I couldn't bring myself to believing that. And after, many studies, about 3 weeks of beam time, we've come to really determine that this is the nuclear spin of holmium. And so within that, within the nucleus, there's spins. The neutron interacts with that, and you see hyperfine interactions. And that's there. And if I'm writing a research grant, I can tell you about quantum technology and quantum information and storage, and you have another memory device in there in the nucleus, and it talks to the electrons, and give me some more money and I'll study it. But I don't believe any of that either. With that, thank you. Yes, I'm around for the weekend and the next couple of days. And as I said, at least if you're interested in neutrons, my neutron slides would normally take an hour. And maybe we can get together over tea or something. All those times.